Hello, welcome to our channel for Python programming. In this video, we will talk about using exponential distributions in Python. So we know exponential distribution is a probability distribution modeling the time between events in a process, and this process is called Poisson point process, which means it has a constant occurring rate in and time interval. And exponential distribution is a special case of the gamma distribution where the shape parameter in the gamma distribution equals 1. So this means exponential distribution is to model the random time until next event time. So this is a random variable modeling the time between events, but exponential distribution only focuses on the next event occur. Until next event occur, what's this random time? So the probability density function for the exponential distribution is quite simple. It has only one parameter called beta. So beta here is actually the mean of this exponential distribution. The beta is the average time until next event occur for this exponential distribution. And the variance of an exponential distribution is beta squared. And it is also that exponential distribution for the random variable only for the positive. For otherwise, for the negative and 0, is 0 for the density, for the probability density. So next we will show how to use several important functions in exponential distribution in Python. So first we will load import module for expon from scipy.stats and the numpy module and matplotlib module. Then first we will show how to generate random variables from exponential distribution. So we can use exponential.rvs and with the parameter scale. Scale here actually is the beta. So here we set the scale 2, which means the average or mean time until next event occur is 2. So now we set size 10 will generate 10 such random numbers from this exponential distribution. So these 10 numbers can mostly between 0.6 and 4.3, 5.4 and 3.0 like this. So it's quite understandable because the mean time is 2 here. The next function called PDF. PDF is to calculate the probability density of random variables from exponential distribution. So first we create an array called quantile, which defines the range of random numbers we are interested in. Then we can use the function called PDF from exponential module. Then PDF quantile of this array, and we set a scale equals 1 here. So here we set the beta equals 1. Then we plot this density curve. So this is an exponential distribution with beta equals 1 for the random variable between 0 and 3. The second function we want to talk about is called cumulative probability, and this function is CDF. CDF, which means the cumulative probability from 0 to a value. So this is to model the probability of x less than a certain value. So same as before, we create quantile array first between 0.01 to 9, and we create a cumulative probability array for this quantile value, and with the same beta parameter 1 here. So we plot this cumulative probability function. So from 0 to 9, can see the cumulative probability is non-decreasing. And if we look at this density, actually this cumulative probability is the integral of this density function. So the first density is very large, so the increase is very quick. The slope is very deep. Then when the density is lower, very slow, very low until 0, there is almost no increasing in cumulative probability. Then we show an example. Use, for example, to calculate the probability of x larger than a certain value. Here we set a larger than 3 from an exponential distribution with a mean value 2. So we want to know, for example, if average of the mean time until next event occurring is 2 minutes in this exponential distribution. And we want to know the probability, how large is the probability that next event occur will larger than 3 minutes. So here we set a scale equals 2, and we use exponential distribution CDF, cumulative probability, with a 3 here and a scale 2. Then we use a 1 minus this object. So which means because exponential CDF will calculate the probability less than 3, right? So here we use a 1 minus this object will return the probability of larger than 3. So the result is about 0.22. So about 1/4 of the chance that the next event occur will larger than 3 minutes from this exponential distribution with the mean occurring time is 2, right? Thanks for watching.